Good afternoon. My lecture is named Thermal Prospecting in Archaeology. The main goal of this presentation is to attract attention to the near surface temperature prospecting. Outline. Temperature measurement in the shallow wells, thermal properties of the archaeological and environmental features, scheme of noises appearing in the near surface thermal prospecting, correction for the temporal temperature variation in the heliothermal zone, correction for the inclined terrain relief, similarity of the thermal and magnetic field, interpreting models, some typical examples from the mining geophysics using the near-surface temperature analysis, examples of the near-surface temperature investigation on archaeological sites, and temperature measurement in well with a 200-300 depth for calculating the climate of the past. Okay, why we do need to measure the near surface temperature? Temperature is independent. Yes. Temperature is an independent geophysical parameter, no less important than magnetic or electric properties. Many archaeological remains differ from the surrounding medium in their thermal properties. For instance, thermal conductivity. Near-surface temperature observations are usually conducted in shallow wells at depth of 1-3 meters. At the same time, the application of this methodology in practice is not frequent. The absence of the following 3 interpretive stages and 1 technical stage limits the wide application of the near-surface temperature survey. First limitation, absence of reliable methodology for removing or reducing the influence of the seasonal temporal variations propagating with some delay from the Earth's surface. 2, simple procedure for removing the terrain relief influence. 3, absence of the normal quantitative procedures for the quantitative analysis of temperature anomalies and the complex physical archaeological conditions, oblique polarization, inclined surface relief, and unknown level of the normal field, superposition of various temperature anomalies. And technical limit is the necessity to drill the near surface boreholes. In table 1 are compiled the thermal conductivity of some rock, environmental features, and archaeological remains. If you will analyze these properties, we can see that we have a sufficiently strong difference between some geological rock properties, between the rock, archaeological remains, and environmental future. So the difference in these properties may be more that we have in the density parameters. Okay. In this block scheme are compiled the disturbances appearing in the near surface temperature measurement. They are divided to the natural and artificial. Artificial is instrumental, second industrial. So sometimes we have influence from some industrial object. About instrumental. Now the precise temperature sensors allow us to measure the temperature with accuracy 0.001. It's a very high accuracy. Natural can be subdivided to the non-stationary and stationary. Non-stationary is a time variations with some delays that going from the episurface. Stationary is a physical geological environment, difficult of the whole drilling, dense vegetation. After this, we have some natural disturbances as geological and archaeological factors. and event topography. And event topography is divided has the twofold. The one, topographic mass effect, and second, the variation of distance from the measurement point to the object of excitation. It's the same that in other geophysical fields. If we will observe object on the inclined surface, we have the different points to the left and right that due to the different inclination of the terrain relief. We have also the complex structure of the geoarchaeological section, the variety of sources, oblique polarization. Oblique polarization is the analogy of the magnetic magnetization, variable surrounding medium, and variety of the touches. Let's begin from the analysis of time variation of temperature observed at the Earth's surface and below the Earth's surface at some levels. What we can see here is this: we have the caves that very experimentally observed at the eastern slope of the Great Caucasus many years ago with my participation. We have here the four types of the temperature cover. The first observed at the Earth's surface, and you see we have a higher amplitude of the temporal variation of the temperature field. We have at the level of 20 centimeters below a surface, we have also significant amplitude of the temporal variations. We have the temperature observation at the depth of 60 centimeters, also is significant. And at the 1 meter, we can see here, but we also have some small variations. What follow from this is that we need to measure the temperature observation at much more deep with the simultaneous calculation of the seasonal variations. For the seasonal variations, we suggested to apply the following formula. What is essential in this formula? That first we need to use some variations that we receive from some temperature station in the vicinity, from meteorological station, from the vicinity of the archaeological studying. And the third, that we need to apply this measurement not one time, several times, maybe 3 times in the different period of time. In this case, we receive the set of algebraic equations that allow us to detect the desired signal of temperature with the required accuracy. What we can see here, influence of terrain relief. We have at the B, this is very well known, the cave after the Lachenbruck, the topographic disturbances on the inclined relief. But if we will compute the magnetic Z component, vertically oriented vector, we receive the similar distribution, but only in the reverted correlation. Only in the reverted correlation. What follows from this? In the magnetic prospecting was developed the procedure for calculation of the inclined relief by the correlation method. We can apply the same procedure for the reducing the terrain relief effect in the temperature prospecting by use of the correlation method, but with inverse sign. In temperature, we have the decreasing of the temperature values with increasing the height of relief. Here you can see the example of the calculation of the terrain correction by the correlation method in one of the gold deposits in Lesser Caucasus. You see its initial cover, its correlation field, its cover after introducing the correction for relief that the two anomalies are directly correspond to the buried or targets. Similarity of the temperature and magnetic fields. This similarity is well known in the we have Fourier law. We have the magnetic field when we have the Poisson law. So we have the theoretical similarity in this field. And we have also, for instance, the similarity for some interpreting model for the Z component in the magnetic field and for the temperature component from anomalous bodies. Taking into account that we have the similarity in this field, we can calculate one new interpreting parameter, temperature moment. Temperature moment can be calculated by the same expression that we have in the magnetic field, but substituting the temperature parameter, for which aim we need to calculate the temperature moment. That for the same aim that we have in the magnetic or maybe gravity method for classification of temperature anomalies. You see, it's very interesting example. Here you can see the calculation of magnetic A and temperature anomalies over the model of inclined thin body. The magnetic anomaly was calculated by using 3D software with for the Z component with the inclination of magnetic field along this bed. The thermal model was physically observed in a tank, in a tank when we have the soil and iron bed, and the iron bed. We have here analogy that we have thermal anisotropy or thermal polarization that is along this iron body. We have the similarity of these anomalies. And when I applied to interpretation of these anomalies, the methods specially developed in magnetic prospecting for complex physical geological conditions, the oblique magnetization or polarization, and the unknown level of the normal field. For the magnetic field, I receive the exact position of the at the edge of the magnetized bodies. And for the thermal body, not exact due to the, you see, so that we have really some small mistakes by the thermal field observation. The interpreting model used in the magnetic prospecting, here we have the most used interpreting model, the model of thin bed, the model of horizontal circular cylinder or sphere, one moment, model of horizontal plate, model of a thick bed, and model occupying the intermediate position between the horizontal plate and thick bed. How, in which case we can observe the temperature anomaly from the buried object?
Не понимаю, как у меня на это хватало пороху. Потому что, мне кажется, у сегодняшней России, которая
Okay. You see, so the relationship was presented by Suryaninov et al. That you see, so the most important that the H0 delete to the R is less than 5, that by this condition we can reliably observe the buried archaeological body. Maybe in some difficult physical, geological physical conditions, this ratio may be not 5, but 4. Okay, this is a model after Moskitsky, and this model was interpreted by, I interpreted this model by the characteristic point method and received the position of the center of the disturbing body. Okay, I will not stop at this anomaly, this anomaly from the magnetics, but it shows that we need to calculate not only oblique magnetization, polarization, but also calculate terrain relief influence. Inclined relief disturbs the anomaly. Only for calculating the polarization and the calculation for terrain relief, we can receive the real position of the center of disturbing body. Here, the observed cover after Zverev et al. Interpretation from my applied the characteristic point method and revealed the epi edge of the polymetallic body after the calculation correction for the terrain relief. This example very performed in the Filichai period polymetallic deposits. Also here was applied the correction for terrain relief, and after interpretation, the A was received the epi edge of the disturbing body. The results of temperature survey at one of asphalt deposits, initial cover after Bareev et al. It was applied characteristic point and tangents method and received the epi edge of asphaltic body, when also very revealed some archaeological remains. This is observed temperature anomaly from Bellerby et al. It was applied the characteristic point method and tangents method and very receives the position of archaeological remains that coincide with the archaeological excavation result. The quantitative examination of temperature profile, the observed temperature after Brevio et al. It also was applied quantitative method, the tangents method and characteristic point method, and receives that the archaeological remain is at the depth about 3 meters. It's very interesting example, the observed and modeled temperature and archaeological model after Moskitsky. What we have here, we have the ancient crypt, we have the observed temperature over this, and we have the modeled by the dot. By the dot, we have the modeled temperature. And here, I calculate the Z component from this model of the magnetic field with a vector oriented downward. And this model is more best coincides with the observed temperature, that's the temperature model. You know, of course, that the Karlslow and Jaeger and this classic book note that the calculation of temperature field is exactly coincide with the temperature of magnetic field. What we have, also Mr. Paparo has successfully conducted near-surface temperature investigation in the remains of the Roman fortress in Netanya city in northern Israel. The previously unknown block made from limestone of the Roman fortress was detected. Unfortunately, I have not permission to present this data. From an archaeological perspective, why do we need to know about the past temperatures? This allows us to trace some important historical and archaeological events and facts. This allows us to obtain some estimates of the parameters of ancient agriculture. This is significant for paleogeomorphological analysis. This allows us to evaluate some physical chemical properties of the ancient building materials. This allows us to draw some conclusions about the ancient natural conditions. This data, along as the physical chemical parameters, can be used to create a 4D database of the past times. I will know to present in detail the methods how we can detect the temperature of past in borehole with a depth of 200, 300 meters. What is important here? First, we need to have the accurate temperature measurement. Second, we need to begin the temperature measurement after some time, at least 4 or 5 times exceeding the time of the drilling of borehole. And the third, the geological section, when we will perform this measurement, must be homogeneous, uniform. If we will apply some formulas, we will receive we can receive the estimation of the past temperature. You can see on this figure the four model of the climate of the past that we receive from one borehole in North America. This investigation can be evaluated. Okay, what I have in conclusions, thermal field analysis in archaeological prospecting is no less important than other geophysical methods. For instance, magnetic resistivity, ground penetrating radar, self-potential. The near surface temperature investigation can be conducted in land, mines, caves, and water basins. Further development of the near surface temperature studies in archaeology and analysis of the climate of the past will give us new, unique information about the buried antique targets and the climate of the past. Thank you for your attention.